You now know about linear regression with multiple variables. In this video, I want to tell you a bit about the choice of features that you have and how you can get different learning algorithms, sometimes very powerful ones, by choosing appropriate features. And in particular, I also want to tell you about polynomial regression, which allows you to use the machinery of linear regression to fit very complicated, even very nonlinear functions. Let's take the example of predicting the price of a house. Suppose you have two features, the frontage of the house and the depth of the house. So here's a picture of the house we're trying to sell. The frontage is defined as this distance. It's basically the width or the length of how wide your lot is, of this plot of land that you own. And the depth of the house is how deep your property is. So there's the frontage, that's the depth. So you have two features called frontage and depth. You might build a linear regression model like this, where frontage is your first feature x1 and depth is your second feature x2. But when you're applying linear regression, you don't necessarily have to use just the features x1 and x2 that you're given. What you can do is actually create new features by yourself. So if I want to predict the price of a house, what I might do instead is decide that what really determines the size of a house is the area, really the land area that I own. So I might create a new feature, and just call this feature x, which is frontage times depth. This is a multiplication symbol, right? So frontage times depth, because this is the land area that I own, and I might then select my hypothesis as that, using just one feature, which is my land area, right? Because the area of a rectangle is, the product of the length of a size. So depending on what insight you might have into a particular problem, rather than just taking the features frontage and depth that we happen to have started off with, sometimes by defining new features, you might actually get a better model. Closely related to the idea of choosing your features is this idea called polynomial regression. Let's say you have a housing price data set that looks like this. Then there are a few different models you might fit to this. One thing you could do is fit a quadratic model like this. It doesn't look like a straight line fits this data very well. So maybe you want to fit a quadratic model like this, where you think the price is a quadratic function, and maybe that will give you, a fit to the data that looks like that. But then you might decide that quadratic model doesn't make sense, because with a quadratic function, eventually this function comes back down, and well, we don't think housing prices should go down when the size goes up too high. So then maybe we might choose a different polynomial model and choose to use instead a cubic function, and where we have now a third order term, and we fit that, maybe we would get this sort of model. And maybe the green line is a somewhat better fit to the data because it doesn't eventually come back down. So how do we actually fit a model like this to our data? Using the machinery of multivariate linear regression, we can do this with a pretty simple modification to our algorithm. The form of the hypothesis we know how to fit looks like this, where we say that h of x is theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3. And if we want to fit this cubic model that I have boxed in green, what we're saying is that the predicted price of a house is theta 0 plus theta 1 times the size of the house, plus theta 2 times the square size of the house, so this term is equal to that term, and then plus theta 3 times the cube of the size of the house, right? So it's that third term. In order to map these two definitions to each other, well, the natural way to do that is to set the first feature x1 to be the size of the house, and set the second feature x2 to be the square of the size of the house, and set the third feature x3 to be the cube of the size of the house. And just by choosing my three features this way and applying the machinery of linear regression, I can fit this model and end up with a cubic fit to my data. I just want to point out one more thing, which is that if you choose your features like this, then feature scaling becomes increasingly important. So if the size of a house ranges from 1 to 1,000, so from 1 to 1,000 square feet, say, then the size squared of the house will range from 1 to 1 million. That's the square of 1,000. And your third feature, x cubed, your third feature x3, which is the size cubed of the house, will range from 1 to 10 to the 9. And so these three features take on very different ranges of values, and it's important to apply feature scaling if you're using gradient descent to get them into comparable ranges of values. Finally, here's one last example of how you really have broad choices in the features you use. Earlier we talked about how a quadratic model like this might not be ideal because maybe a quadratic model fits the data okay, but the quadratic function goes back down, and we really don't want housing prices to go down to predict that as the size of the house increases. But rather than going to a cubic model, you have maybe other choices of features, and there are many possible choices. But just to give you another example of a reasonable choice, another reasonable choice might be to say that the price of a house is theta 0 plus theta 1 times the size, and then plus theta 2 times the square root of the size, right? So the square root function is this sort of function, and maybe there will be some value of theta 1, theta 2, theta 3 that will let you take this model and fit a curve that looks like that, and goes up but doesn't, but sort of flattens out a bit and doesn't ever come back down. And so by having insight into, in this case, the shape of the square root function and into the shape of the data by choosing different features, you can sometimes get better models. In this video, we talked about polynomial regression, that is, how to fit a polynomial like a quadratic function or a cubic function to your data. And we talked about this idea that you have a choice in what features to use, such as that instead of using the frontage and the depth of a house, maybe you can multiply them together to get a feature that captures the land area of a house. In case this seems a little bit bewildering, that, wow, we have all these different feature choices, so how do I decide what features to use? Later in this class, we'll talk about some algorithms for automatically choosing what features to use, so that you can have an algorithm look at the data and automatically choose for you whether you want to fit a quadratic function or a cubic function or something else. But until we get to those algorithms, for now, I just want you to be aware that you have a choice in what features to use, and by designing different features, you can fit more complex functions to your data than just fitting a straight line to the data. And in particular, you can fit polynomial functions as well, and sometimes by appropriate insights into the features, you can get a much better model for your data.